Hey guys, welcome to GeeklyEDU Chemistry, and this is Sona saying today we are going to talk about the nuclear reactions and the various types. But before we do that, I hope you remember the last class where we talked about the decay and we gave you a problem to solve, right? So you had around 0.257 mg of a lead in a sample and 1 per milligram of uranium 238, right? And the half-life was given 4.5, and you were asked how old the rock is. So let's find out. So presently in the rock you have lead 0.257 mg and uranium 1.000 mg. Originally what would have been, we are assuming that there is no other source of lead, so lead was 0, but uranium was present 1.000 plus the amount that is now decayed. Now we can't simply add 0.257 because the mass of uranium is more, so we make the ratio to 38 upon 206, right? And we come out to have 1.297 mg. Now T half is 0.693 by K, so you get the K first order kinetics, simple funda, right? So you have 1.5 into the power minus 10 per year, that's your K. Now you use the integrated rate equation log ln A naught upon A equals KT. I hope you remember that, right? So we apply the same equation here. We plug the value of K. We don't know T. We want to find out T. And if you do the math, it comes out to be 1.7 to the power 9. That's how old the rock is. That is how we calculate from the decay. Now let's talk about transmutation, fusion, and fission, which is the topic of this particular video. So transmutation or artificial transmutation is you're mutating an element, you're changing one element to another. Now how do you do that? You bombard it by highly charged particles. Rutherford was the first guy to do that. He bombarded alpha particles, that is He2 plus particles, in the nitrogen atom, and he got hydrogen in another form of oxygen. Now the problem is whenever you want to bombard this He2 plus particles, you need to use complicated machines called cyclotrons, because He2 plus is positive, nucleus is positive, right? So you use these two Ds, right? These two Ds have a high frequency AC current, and when an He plus particle goes around, because of the magnetic field, it gets more and more velocity, and finally you allow it to come out, and this is very, very high energy beam carrying particles with high energy. One of the largest facilities like this is at CERN, right? So these cyclotrons are huge machines where you collide these charged particles and you generate or transmutate the elements from one to another. Switzerland facility, which you see right now in this picture, this is the white line represents the LHC in the at CERN right now, but the further plan is a whole lot bigger, but it will be ready only by 2040. Now let's talk about fission. Fission simply means to split. Uranium 235, you bombard it by a neutron, it's very easy, and that would split to form another elements, right? Now the thing is, whenever such things happen, it ends up emitting more neutrons and obviously energy. Now some are spontaneous, they don't need an activation energy, whereas some might need an activation energy to overcome the binding energy. If you remember in the last video, check it out if you have forgotten that, right? Now almost every element with atomic number more than 80, they have one of the more isotopes which go for fission, right? Now the neutrons that you generate can collide with the next fissionable atoms, and hence what can happen is the product becomes a reactant in the next step, right? As you can understand, this is what we call a chain reaction. Now, do we want chain reactions? Yes, but it will only happen if you have a critical mass, because there should be enough fissionable atoms. But can we allow chain reactions to go uncontrolled? No, we need to control these reactions, because if the amount of energy being produced goes on and on and on, we can destroy ourselves. So that is why we need to control the heat by cooling down, or we need to have control rods that will absorb some of those neutrons, like that of cadmium boron. We use this to generate electricity, and as you can see, 19% of energy from United States come from this. So you can see these control rods. This is a nuclear reactor, thanks to the US Department of Energy for the schematic diagram. So those were the control rods and how they control the fission reaction. Now I'll quickly talk about fusion. Now fusion means combining. So let's imagine two hydrogen atoms combining together to form a helium atom, right? So again, that requires a huge amount of energy, right? So two lighter nuclei combine to form a heavier nuclei, but the energy released is much more. This is what occurs in the sun thanks to the spectrophotometric measures that we have taken. So in order for a nuclear fusion to occur, you must provide it the temperature, which is around 40, 100, 40 triple zero triple zero Kelvin, right? This is what happens in thermo bombs or hydrogen bombs. Now there's a question for you. You have already calculated the age of the rock, but I want you to understand what is the logic that we use behind dating using carbon C14 in live fossils. Try to answer in comments.
We hope you like this video. Press subscribe, thumbs up, and stay geekly.